If you've spent any time around MRI, you've probably heard this term K-space thrown around. It often sounds like this super complicated, mysterious step that you just have to accept. Well, today we're going to pull back that curtain. We are going to make K-space make sense.
Okay, so let's just get right to it. On the left, you're looking at the raw data that the MRI scanner actually collects. This is K-space. And yeah, it kind of looks like a starburst filled with static. On the right, that's the final crystal clear image of a brain. And that's the big question, right? How in the world does that on the left turn into this on the right? So that is our core question for today. What is this bizarre-looking data, and how does it contain the secret recipe for such a detailed picture? Think of this explainer as a journey to solve that puzzle. And by the end, trust me, you'll see that K-space is actually surprisingly intuitive.
All right, first things first. We need to figure out how this grid of data gets built in the first place. It doesn't happen all at once. It's built piece by piece, or more specifically, one echo at a time. So, just a quick refresher. Remember that in MRI, we send in these radio frequency pulses, and that causes the tissue to send a signal back out. We call that returning signal an echo. Now, here's the key thing to get. That echo isn't a picture. Not yet, anyway. It's just a wave, a stream of raw data. The scanner's job is to listen to that stream, sample it, and carefully place those data points into a big grid. And this is the absolute rule. One entire echo is used to fill one single row of K-space. It's a direct one-to-one deal. You got an echo, you fill a line. That's it. So if you want an image that's 256 pixels high, well, you're going to need 256 echoes to fill those 256 rows. So to fill the whole grid, the scanner just runs the sequence again and again and again. But each time it does something slightly different. It applies what's called a phase encoding gradient. You can think of this gradient as giving each echo a unique address, telling it exactly which row of K-space to go to. See? The echoes with no gradient go right to the middle, and the stronger the gradient, the further out to the edges the data goes.
You know, this line-by-line process brings up a really important question about timing. If we're filling it one row at a time, how long does this whole thing actually take? And here's where it gets really interesting. Filling one single row, just listening to one echo, is ridiculously fast. We're talking about 8 milliseconds. But to get ready for the next row, we have to wait for what's called the repetition time, or TR. So filling all 256 rows can take several minutes. This huge time difference is exactly why if a patient moves, the artifacts are almost always in one direction, the slow direction, the one that takes minutes to build.
Okay, so now we know how K-space is built. Now for the fun part. What does all this data actually mean? What's the difference between the information in the center and the information out at the edges? Let's start with the very center of K-space. It's obvious that the signal is way brighter here. The amplitude is highest. So why is that? Well, because this data is collected with zero phase encoding gradient. Without that gradient causing all the little signals to get out of sync and cancel each other out, the echo comes back at its absolute strongest. All the powerhouse data is packed right into the middle. This is like a fundamental law of MRI physics. As the source material says, the center of K-space always contains maximum signal. It's the most important rule to remember. All the strongest, highest quality information lives right here. So what would happen if we tried to make a picture using only this super strong central data? Well, you get this. It's a picture, kinda. It's blurry, there's no sharp detail, but look, it gives us the basic overall shape, and most importantly, the fundamental contrast of the image, what's bright and what's dark. Which of course leads to the most obvious question. If all the good stuff, all the strong signal that gives us contrast is right there in the middle, why on earth are we wasting all that time collecting the weak, faint data way out on the edges? And here is the mind-blowing answer. When we build an image using only that weak data from the periphery of K-space, this is what we get. There's no contrast, no sense of light or dark, there's just edges, fine lines, sharp outlines. All the high-resolution details live out here on the edges. So you see, the center and the periphery have totally different but equally important jobs. Think of them as a team. The center is the heavy lifter, giving you the high signal contrast and the basic shape. The periphery is the artist, coming in afterwards to draw all the fine, sharp, high-resolution details. You need both to get a proper image. All right, final piece of the puzzle.
We have our beautifully organized viewprint of contrast and detailed data. How do we actually build the house? How does the computer translate this map into the anatomical image that we can actually look at?
To get this, we just need one term: spatial frequency. Here's an easy way to think about it. Imagine a sandy beach. A big, gentle dune that changes slowly over a long distance. That's a low spatial frequency. A tiny, sharp ripple in the sand that changes very quickly. That's a high spatial frequency. K-space is literally a map of all those dunes and ripples in the patient's body. The center holds the low frequencies, and the edges hold the high ones.
The entire reason we go through all this trouble, the frequency and phase encoding, organizing data in this specific way, is so we can use an incredibly powerful mathematical tool called the Fourier transform. It's the magic key that unlocks the image hiding inside the K-space data. The best analogy for the Fourier transform is that it's a perfect universal translator. K-space speaks the language of frequencies, how often things change. The final image we want to see speaks the language of locations, what is where. The Fourier transform simply translates flawlessly from one language to the other. And check this out. This is such a great way to visualize it. K-space isn't just a flat map. If you imagine signal strength as elevation, it's a whole landscape. There's this massive mountain peak of signal right in the center that slopes down to these low, flat plains out at the periphery. The Fourier transform analyzes this entire landscape to build the image.
So we've gone from a weird starburst of data all the way to a medical image. But why does this actually matter? Why is this not just some academic exercise? Why should you care about this in the real world?
Because it's all about making MRI faster and better. Once engineers understood that the center gives you contrast and the edges give you detail, they could start inventing clever shortcuts. All the modern fast scanning techniques are basically just fancy, creative ways of filling K-space more efficiently, like using a spiral path to grab that important central data first. This knowledge is what drives innovation.
And that leaves us with a really fun idea to chew on. Now that you know the blueprint, think about the possibilities. If the center gives you contrast and the edges give you detail, what if you could play Frankenstein with K-space? What if you took the center from a T1 weighted scan and stitched it together with the edges from a T2 weighted scan? What kind of weird hybrid image would that even create? See, understanding the blueprint doesn't just solve a mystery, it lets you imagine what's next.